We'll wait for more 5 minutes, then we'll start. So can we start now? Am I audible? Hello?
Yes, sir.
Okay, so can we start now?
Okay, sir.
Yeah. My screen is visible?
Yes, sir.
Okay, fine. Okay, good afternoon everyone, and this course is for the mechanics of machining. We have already discussed week 4 lectures and the tutorials. We have seen the tutorials. We have solved different problems related to the different topics in this 4 weeks. Now we will be seeing the week 5 contents, which has been already taught in the class. So first we'll see the content, what all we are going to discuss today. So in lecture 1, we will discuss about the thermal aspects of machining. In lecture 2, we'll discuss about the tool wear and tool life. And in lecture 3, we'll discuss about the optimization of machining process. So I'll give a brief idea and or a brief revision about the things which have been already taught in the class, and then we'll move to the tutorial class in which we will solve some of the numericals. So okay, then I'll begin. If anyone have any problem, any doubt, please ask me. We'll see that. So before starting, the last year assignment, which is assignment 4, have you solved it? Have you solved the assignment 4?
Yes, sir.
So you were able to solve every question, right?
1 or 2 questions, sir. Not solved.
So you have any doubt regarding that? We can discuss it.
No, sir.
Okay, fine. Okay, fine. Then we'll begin our tutorial class for week 5. Okay. So the first topic is the thermal aspects of machining. See, whenever you are doing any machining, what is machining? Machining is basically a physical contact between two materials. One material being the tool, one material being the workpiece, right? So whenever there is the contact between two material, whenever there is some sliding between two material, then there will come the role, then there will be a role of friction between them. So whenever friction come into picture, then because of that friction there is some increase in temperature, the increase in temperature between the interface of the two material. So that increase in temperature of the workpiece or of the tool or of the chip, anything that has to be studied in a very detailed manner, because the increase in temperature of the workpiece or of the tool or the chip give us different ideas of the process. We can relate this increase in temperature with the force, with torque, with power, with the workpiece surface finish, and many other things. So this thermal aspects of machining is one of the very critical criteria of judging how your machining was or how the process parameter came out to be. Okay, so first of all, when we do a machining, talking about the simple single point cutting tool machining, so when we'll do that, so there are basically three distinct regions of heat generation. See, one is the shear zone, one is the chip tool interface zone, and one is the work tool interface zone. See, please see this figure. Okay, please see this figure. You can see there are three zones. One zone is A, one zone is B, and one zone is C. So A zone is called the shear zone. See, this A zone is called the shear zone, right? Second is the chip tool interface zone, which is the B zone, which is shown here, and third is the work tool interface zone, which is called the C zone. So we will see what does this three zone means, or what does it signifies. See, so whenever a tool machines a workpiece, right? Whenever a tool machines a workpiece, then first step is what? First step is what? Is the plastic deformation of material. So after the plastic deformation only, chips get sheared. Chip gets sheared from the workpiece and it starts flowing on the rake surface, right? So this A, the region where the chip gets sheared, is called the shearing zone, right? Second, now the chip has been formed, it has been plastically deformed, it has been sheared. Now the chip flows on the rake surface. This is the rake surface, this is the rake surface. Now chip flows with a velocity Vc on the rake surface. So that region on which the chip flows is called the chip tool interface zone. And third, there is also a contact between the machine surface and the tool, right? There is always a contact between the workpiece and the tool. So therefore we are applying a clearance angle, right? Therefore we are applying a clearance angle so that the friction between the tool and the workpiece reduces. So but there is, however, some sliding between the tool and the workpiece. That zone is known as work tool interface zone. So basically we have three zones, we have seen that. Now maximum amount of heat generated is you can see in the A zone, in the shear zone, and then into this tool, and third B zone, and third in the C zone. So if you want to like make a brief summary ki how much heat is generated and which material or chip or tool is carrying what amount of tool, then the maximum amount of tool heat, which is the 80% of the heat, is carried out by the chip. See, basically we have three entities. One is the tool, one is the workpiece, and one is the chip, right? The maximum amount of heat is carried out by the chip, which is around 80%. Second, heat will also get generated in the tool, so the 15 to 20% of the heat flows into the tool. And third, the minimum amount of heat, which is around 5%, get conducted to the workpiece. So basically out of 100%, 80% goes into the chip, 20% goes into the tool, and 5% around goes into the workpiece. Therefore, the study of chip becomes very important in determining the thermal aspects of machining. Now, what are the variable affecting the cutting temperature so there are different variables which are affecting the cutting temperature. Mostly variables are the process parameters which are affecting the cutting temperature. So we'll see them one by one. See, three most important variables are cutting speed, cutting feed, and depth of cut. These are written in order. the number one variable which mostly affect the temperature is the cutting speed. Second is the feed rate, and third is the depth of cut. So these are the most important process parameter which affects the temperature. If you will change the speed or feed or depth of cut, if you will change any three of it, then the cutting temperature will change, and the cutting temperature will change. It depends how it varies with the speed, feed or depth of cut. And the most important or the most significant variable is the cutting speed, because the cutting speed has a very huge impact on the cutting temperature. So this we have seen ki basically we have three region. One is the shear zone, one is the chip tool contact zone, and one is the work tool interface zone, in which the chip carries the maximum heat, second is carried by the tool, and third is carried by the workpiece. This is all about the zones in the machining where we can see the thermal aspects. Okay, this is fine. So I should move to the next slide. Now,
Okay, sir.
yes, okay. So now if some sliding is happening, right? Some sliding is happening. Some friction is developing. Some forces are acting. So we have already seen the forces, right? We have already seen the forces. For example, this is a tool. This is a tool. This is a chip which is flowing. This is the workpiece. This is the workpiece, right? This is the workpiece. This is the workpiece. This is the chip, and this is the tool. So basically, what all forces you are getting? Where you are getting one shear force on the shear region. For example, this is the shear region. Then you will get a shear force Fs, right? One is the friction force, because chip is flowing on the rake surface. Then the friction force will come to oppose the flow of chip. Then the friction force will also act on the rake surface opposite to the flow of chip. So if the chip is flowing in this direction with the velocity Vc, then friction will act opposite to it, which is F. 1 second. Someone is joining. Okay, so what I was telling about कि whenever a tool, chip and workpiece come into contact, so we have this shear zone in which a shear force act, a chip tool interface zone where the chip flows on the rake surface. So because of the flowing of the chip, some friction come into contact, this F, right? So, and one is the cutting force, which obviously cut the material, right? Which is the main component, which is the cutting force. So basically we have three forces. One is Fc, which is the cutting force, One is the F, which is the friction force, and one is the Fs, which is the shear force, right? Which is the shear force. These are the three major forces which are responsible for the power consumption. So whenever a chip flows, first, what is the first step? First step is the shearing of chips. First step is the shearing of chip. So here power will be consumed because of the chip, power consumed here. Second will be this flowing of chip into the rake surface. Here also power will be consumed, right? Here also power will be consumed. And one is the total cutting, because the ultimately tool is cutting the workpiece, then because of the cutting, then there will be power will be consumed. So our main aim is to find this power and minimize the power, so that ultimately we want the power to be minimum, right? Because if the power will be minimum, then less force would be required and our energy will be saved. So our main aim is to determine the power consumed, total power consumed, and minimize it for the better machining. This is basically the things we need to see. Now we'll see how this power is calculated. So I'm going to rub it. Okay, fine. See, so total power consumption in the machine is given by Fc into V, right? Fc is the total cutting force and V is the cutting velocity. So if you want to find a total power, then you just need to, what is the formula of power? Power is F into V. So for total power, you need to find the cutting force and the cutting velocity. So we should find Fc and V, and then we can find a total power. Now this total power is the combination of two power. One is PP and one is PS. What are PP and PS? PP is the power dissipation in the primary deformation zone, and PS is the power dissipation in the secondary deformation zone. Now, what is primary deformation zone and what is secondary deformation zone? See, the PS, which is a secondary deformation zone, is the zone where the chip flows on the rake surface, right? So basically this PS is the power consumed because of the chip flowing on the rake surface. So what you want, because on the rake surface which force act? Friction force act, right? We have seen here, see, we have seen here on the rake surface friction force is acting. So this friction force into chip velocity is equal to F into, basically it is F into VC. VC is the chip velocity. But also we know, one second, someone is joining, one second. Okay. My screen is visible, right? My screen is visible. Hello? Hello?
Sir.
Okay, fine. So basically what I was telling, the total power consumed is Fc into V, where Fc is the cutting force and V is the cutting velocity. But this total power can be divided into two power. One is PP and one is PS. So PP is the power dissipation in primary deformation zone, and PS is the power dissipation in the secondary deformation zone. Now, what is primary dissipation zone and what is secondary deformation zone? See, we have already discussed the primary deformation zone is the shear zone, and the secondary deformation zone is the zone where chip flows on the rake surface, right? So, in the primary, the PP can be find out using the shear force and using the shear velocity Vs. Very simple. Similarly, the PS, which is a secondary deformation zone, which is act because of the friction, can be found using the friction force and the chip velocity Vc. So we know this. We just need to find the friction force and the friction velocity, and this is for the shear zone. This is for the shear zone, and this is for the chip rake surface zone. Chip rake surface zone. So the primary power dissipation can be found using the friction force and the shear force and the shear velocity. And the secondary deformation zone can be found using the friction force and the cutting velocity and the chip velocity. This we need to find so that we can find the power consumption. This is very simple. Now I'll show you the formulas. See, the PS, which is the secondary deformation zone, can be found using the friction force F into chip velocity. Now we also know that Vc by V, Vc is the chip velocity, V is the cutting velocity, is equal to R, which is the cutting ratio. So therefore Vc can be found into V into R. So similarly I have written this PS is equal to F into Vc, where Vc is equal to V into R, to F into V into R. So therefore we can find this power consumed in the secondary deformation zone by the formula F into V into R. Similarly, either you can find the value of PP using Fs into Vs, or simply we can find the value of PP is equal to total power minus P of secondary. Any way you can find. either you can calculate the shear force and multiply it with the shear velocity, so you will get the power consumed in the primary deformation zone, or you know the total power, which is Fc into V. You subtract it with the chip power, which is F into Vc. If you subtract it, you will get the power consumed to the primary deformation zone. So anyway, you can calculate the power, right? Can I move to the next slide?
Yes, sir.
Okay. You do anyone have any doubt? Please, if you are having any doubt, please ask me so that we can clear it right now. Okay, then I'm moving to the next slide, right? This one thing is, you can see this we have already seen our last class, ki what is the relation between the chip velocity Vc and V, cutting velocity, and what is the relation between the shear velocity Vs and the V. 1 second, someone is joining. So by using this relationships, we can find the velocity. Like if you know the V, then we can find Vc, and if you know the Vs, we can if you know the V, we can find Vs. So anyway you can solve. So basically you can do anything. You can calculate the forces multiplied by V and find the power. This is the major concept. Okay. Now we'll move to the next slide. What is the role of variation of different machining parameters on cutting temperature? We'll see ki what are the different parameters which affects the cutting temperature. Okay. See, the machining parameter, there are basically 5. It is divided into 5 machining parameters. One is the work material, one is the cutting tool material, one is the process parameter, one is the tool geometry, and one with the environmental factors or external factors. First, we will see one by one ki what are the different parameters of the particular parameter which can affect the temperature, cutting temperature. So first is the work material. See, basically what you are using in the machining, one is a tool, one is the workpiece, and the chip coming out of the work of the machining. So work material play a very important role in which affects the temperature of the process parameter of the machining. And what are the various factors or various points in the work material which can affect the machining parameter or the cutting temperature? One is the specific energy. What is the specific energy of the work material which is required to deform the workpiece? Second is the ductility. How ductile is the work material? Because ultimately when you are cutting the workpiece, then the workpiece has to plastically deform, right? The workpiece has to plastically deform. So then only the dislocation will move, and the chip will ultimately, the shearing will happen and chip will form. So ductility is one of the most important factor. One is the conductivity. How conductive is the workpiece so that it can transfer the temperature. It will not keep the temperature. It will transfer the temperature from throughout its body. And one is the diffusivity. So these are the 3-4 factors in the work material which play a very important role in determining the variation of cutting temperature: specific energy, ductility, conductivity, and diffusivity. Now, the second important parameter is the cutting tool material. Now, you have seen about the workpiece material. Now, you should see about the cutting tool material. So, cutting tool also should have such material so that it would help in the machining for a better machining, for a better output. So one is the thermal property. The thermal property of the cutting tool, or the thermal properties of this cutting tool material, should be very good. It should be thermally very stable so that it should not accumulate heat and loses its property. because that will, if the tool is not that heat resistance, so heat resistant, if you machine for some time and the tool becomes so hot so that it loses its thermal stability, and then the tool loses its all its property, and it's not able to machine properly, and the tool life reduces. So it should have better thermal property. Second is the chemical stability. It should be chemically inert, so that when you are machining a workpiece, it should not change its property. And third is the wear resistance. It is the most important property for any tool, because when you are cutting a material, obviously some forces will act on the tool, right? And the wear will see what are the wears and type of wear later on. So it should be very wear resistance. Third are the process parameter. What are the process parameter to be used so that the proper cutting temperature has to be stabilized? We have already seen that the cutting velocity, the feed rate, and the depth of cut. These are the three most important process parameter which are required for the proper balancing of the cutting temperature. We should keep this three process parameter very optimum, so that there should not be the highly increase in the cutting temperature. Now, fourth comes the tool geometry. Then tool geometry also plays a very important role, because there are different tool geometry, like the rake angle, the cutting edge angle, the clearance angle, and the nose radius. How they play a very important role in the tool geometry, we'll discuss further on. And then comes the environment. What are the cutting fluid you are using? What are the thermal properties? What are the lubrication properties? So this all factor need to be understood very very thoroughly, so that we can study the variation of this parameters with the temperature. Okay, now we will see each and everything in detail. See, role of variation of different machining parameter on cutting temperature. See, we can see a graph where is the one in y-axis we have the temperature, and in z-axis, in x-axis we have this cutting speed Vc, feed S0, and T, depth of cut. So we can see whenever we are increasing this, any three of them, the cutting temperature is increasing. See, with Vc also it is rising, right? With feed also it is rising, and with depth of cut also it is rising. So with increase on everything, the temperature increases. See what happened, and out of these three we can see the cutting velocity has a major impact. See, the cutting velocity curve is graph is at the highest, at the top level. This means, one second. Hello. Yes. So when out of three, we can see that the cutting velocity has a major impact on the temperature. Like for a same increase of, for example, if you are seeing to this point, for this point, you can see the increase in temperature for V is very high. Second is the feed, and third is the depth of cut. 1, 2, 3. So the temperature here is this much, temperature here is this much, and temperature here is this much for a same value of x. So this T1 is greater than T2 is greater than T3. T1 correspond to the cutting speed, T2 correspond to the feed, and T3 correspond to the depth of cut. So the impact of cutting speed is very highest with respect to the temperature compared to feed, then compared to depth of cut. Now, a very important explanation is that how with increase in velocity this cutting temperature increases. So you can see that we know that power, right? Power is equal to F into V, right? So if you are increasing the velocity, see, if you are increasing the velocity, right? If you are increasing velocity, then power will increase, right? The power will increase, and when the power or the energy consumed is increasing, this means the temperature is increasing. Right? Therefore, with increase in velocity, there is a huge increase in the power or the energy consumed, which is leading to the increase in temperature. Therefore, with increase in the cutting velocity, there is a very high increase in the temperature. So this is basically a trend of we see S naught and T with the cutting temperature. Okay, so do you have any doubt regarding this? Hello? Hello?
No, sir, no doubt.
Okay, fine. So I'm now moving to the next part, which is the effect of tool geometry on temperature. Now we'll see the variation of different angles like the rake angle, clearance angle, side cutting edge angle, and the nose radius with temperature. How with this increase in this parameter the temperature is increasing. So first we will see rake angle. You can see here, as the tool rake angle increases, the average cutting temperatures decreases. You can see it is decreasing. Can anyone tell me why it is so? Why with the increase of the rake angle, this average cutting temperature decreasing? Why?
Increasing rake angle, power consumption is decreases.
Why it is so?
Then temperature also.
Why power consumption decreases increasing rake angle?
Sharp edges are on the tool.
Okay. Right. Yeah, you're right. If you're increasing the rake angle, then we know power is equal to F into V, right? Then the force, because of the sharp edges, this force decreases. Right? When the force decreases, then because of the decrease in force, the temperature also the power because of the decrease in the force, the power decreases, and because of the decrease in power, the temperature decreases. This is the reason when we increase the rake angle, the average cutting temperature decreases. Fine. We will see कि then someone will say कि okay, then I will keep the rake angle very high. Then why we are not keeping rake angle that high? Can anyone tell me this? If by increasing the tool rake angle only, the temperature, power reduces, force reduces, ultimately the tool temperature reduces, then why we are only keeping an optimal value of the rake angle? Why? See, you might have seen the numerical, the maximum value of the rake angle is kept up to 10 degrees only. 10, 12, 15 degrees, not more than that. Why we are doing so? Why we are not keeping rake angle value 30 degrees, 40 degrees?
Strength of the tool decreases, sir.
Yeah, very good. Yeah, very good. Because what happens? See, this is a tool, right? This is a tool, है ना? And this is the rake angle alpha. This is the clearance angle, which is equal to gamma, and this is the tool angle, which is psi. है ना? Alpha is rake angle, psi is tool angle, and gamma is clearance angle. We can see alpha plus psi plus gamma is equal to 90 degrees, right? And psi equal to 90 minus alpha plus gamma, and psi is the tool angle. So more is the psi, more strength is of the tool. So if we'll increase the alpha more, if I increase the alpha more, the psi will decrease, and because of this decrease in psi, the tool strength will decrease. Therefore, I cannot increase alpha to after a particular extent. So because of this, we are keeping alpha to optimize to some values, which is around 10 to 15 degrees of angle. Okay, fine. Now we'll see the tool clearance angle. See, it also almost follows the same pattern only. With increase in temperature, clearance angle, the tool temperature decreases. Because if we are increasing the clearance angle, then the gap between the tool and the workpiece is more, right? So if that gap is more, then the less. For example, this is a tool. This is a tool, right? And this is the workpiece, and this is a tool, and this is the clearance angle gamma. So if this gamma increases, then the the gap between the tool and workpiece increases. Because of that, the friction reduces. If friction reduces, then the power consumed by the friction also reduces. Because of that, temperatures reduces. So because of that, when we increase the clearance angle, the tool temperature reduces up to a particular extent. Then after that, other phenomena takes place and it increases again. Okay. Next is the cutting edge angle. We can see here, with the increase in cutting edge angle, the cutting temperature increases. Hello? Can anyone explain me why it is happening with increasing cutting edge angle, how the cutting temperature increases? Hello? Can anyone tell me? Do you have any idea why it's happening? No idea? Okay, so I am giving you this homework. I want in the next class, please you come and find out कि why with the cutting edge angle increases the cutting temp. It is very easy. It is very easy. But I want you to search and understand कि why this is happening actually. कि with the increase in the cutting edge angle, how the cutting temperature increases. If you will not able to find out, we will discuss in the next class. Okay. Now is the fourth point, which is the nose radius. With increase in the nose radius, the cutting temperature decreases. This is why, because we know that we have surface roughness. Surface roughness is equal to f square by 8r. This you might have heard this formula. Surface roughness is equal to f square by 8r, where f is the feed and r is the cutting edge radius, nose radius. So when you are increasing r, then the surface roughness is decreasing, right? When you are increasing r, the surface roughness is decreasing, and the surface roughness is mainly higher because of the higher temperature. So when you are reducing r, increasing r, you are increasing r, then surface roughness is decreasing, which means that the cutting temperature is lower. So therefore, with increase in the nose radius, the surface roughness decreases, corresponding to the decrease in the cutting temperature. Fine? Is it okay?
Okay, sir.
Okay. So we'll move to the next slide. Now, we have seen about the variation of different factors and parameters with the cutting temperature. Now, because of the increase in the cutting temperature, we will see now what is happening to the tool. Because see, tool is a very important part of our machining. Because if tool is only not good, tool has not good properties, then the proper machining will not take place. So here, two very important aspects of tool we are going to see. One is tool wear and one is tool life. First of all, tool wear. So what is tool wear? We have the definition. The tool wear is the failure of cutting tool due to repeated operation and loss of material from the surfaces in sliding contact. See, this is a tool, right? You start machining. This is a fresh tool. You now machine this tool with a material. Now you will see some material will getting chip off. For example, here some material will getting chip off. It will start removing from here. This is pass 1. So this material which is getting removed or lost, it is called the wear. This is only called the tool wear. So we want this to be minimum, because more will be the tool wear, less will be the life of the tool. So this is tool wear. What are the various reasons for tool wear? Adhesion, abrasion, erosion, surface fatigue, gross failure, high cutting temperature. There can be any reasons, right? Different reasons. Because of the very high temperature, the tool will become soft, right? The tool will become soft, and ultimately when it will strike the workpiece, it will get peeled off. For example, when you are writing with your pen, you just you take a lighter or some matchbox and put your pen in front of the matchbox. You will see after some time the your pen will become very soft because of the heating, and then you touch that pen with some some table and all, it will get removed, it will break, right? So that is a wear of that particular pen. Similarly, because of the very high temperature, the tool temperature increases and it becomes very soft, and ultimately during machining it get weared off or chipped off. This is called tool wear. Now we will see some different types of tool wear. So one is adhesion. What is adhesion? See, basically adhesion, from the name only it is showing ki adhesion means कि some other material is getting added to the tool surface. For example, one second. This is tool, right? This is tool, and this is workpiece. This is tool, and this is workpiece. So when you are machining it, the interface between workpiece and tool, there is very high temperature. So sometimes what can happen, some material from the workpiece can be welded to the tool material. So now this is tool. Now some extra material, which is the workpiece material, get welded to the tool material. This is called adhesion. This is also one type of wear. And in adhesion we have two types of adhesion. One is the adhesive wear and one is the galling wear. So what is adhesive wear? In adhesive wear, what happens? The tool has a sharp edge, right? Tool have a sharp edge. For example, tool have a sharp edge. Because of this adhesive wear, the tool sharp edge become round. Tool edge become like this now. See, it is very sharp and it has become round now. So this is a kind of wear. So because of this roundness, the tool will become blunt, and the tool become blunt, then the proper cutting will not take place, and the tool proper cutting will not take place. Your output will decrease. It is a type of adhesion wear. It is called adhesive wear. One is galling. What is galling? When large particles are removed, the removed particle, they stick to the other surface. For example, when you are as I told previously only, when you are removing some workpiece from the tool, instead of going away, it is adhering to the tool surfaces. This is called galling. Basically, with this we have already discussed. In adhesion, we have two wear, which is one is adhesive wear, in which the tool edge become blunt, and one is galling, in which the workpiece material get welded to the tool material. Now, second type of wear is the abrasion. What is abrasion? What is abrasion? Abrasion means, you have seen when you are scratching on a hard material, so some scratch marks come into that material. That is called abrasion. When tool is having machining, if the tool is not that hard, then the scratching marks or some marks will come into tool material. For example, this is a tool, and because of the hard material, hard workpiece, some marks can come here. Some marks can come on the tool surface. This is called abrasion. This is one type of the wear. Now third is diffusion. What is diffusion? Diffusion is some like when you are machining two surfaces, and two surface combine. For example, this is workpiece and this is tool. Because of the very high temperature, these two surface combine, and the proper machining don't take place. This is called diffusion. So basically, these three are the type of wear in which the tool life reduces and the tool quality reduces. So this is okay. Do you have any doubt?
No doubt.
Okay, fine. Now we'll go to progressive tool wear. So what happened? Basically, you will see in the tool, these were the types of tool wear. But you will see in the tool, when you will do machining, there are two types of wear which increases or which continuously progresses as the machining goes on. So one is the flank wear. This wear takes place on the flank face of the tool, and one is the crater wear. This takes place on the rake surface of the tool. See, this is the rake surface, this is the rake surface, and this is the flank surface. So both are in contact with the rake surface is in contact with the chip, and the flank surface in the contact with the workpiece, the machine part. So because of that contact, obviously temperature rise will increase, temperature will increase, then the friction will come into picture, and because of that wear will come. So the wear which happens in the flank surface is called the flank wear, and wear which happens in the crater surface is called the rake surface, called the crater wear. So studying about the flank wear is the most important wear in the tool. We are mainly concerned about the flank wear only. When we are considering the tool life, or to determine the tool wear life, we basically or mainly see the flank wear, because if flank wear reaches the certain value, we see that the tool life is over. For example, I'll give you the value. If the flank wear reaches around 0.35 mm, 0.35 mm flank wear, around 0.2 to 0.3 mm something, then if the flank wear reaches this value, then you can consider that machine tool life is finished, tool life over. This is some standard value which you can find from the reference. However, above this value also tool can work, but standard, if this wear reaches this value, we consider that the tool life is finished, right? And we then don't use that tool. So basically how the flank wear work, see, when you are machining the tool, so the flank wear mainly occurs in three regions. One is region number 1, this one is region number 2, and one is region number 3. The region number 1 is called the initial wear zone. When the tool is in contact with the workpiece, initially it is very active at the early stages. So the wear increases very rapidly. See, you can see that the wear is increasing very rapidly, very highly, very at a very faster rate. But what happens after a certain time, the tool become compatible with the workpiece or the machining environment. So the wear is become steady or uniform. From here to here you can see the wear is very steady, it is not increasing very drastically. And after that, when a point reaches, when you further increase do the machining, it becomes very high, very accelerated tool wear comes. This three. So this three are basically the three stages of the flank wear. One is the initial wear, which is very high, and second is the uniform wear, which is very stable, and third is the accelerated wear, which after that the tool wear become very high, and if will continue machining, then tool will become unstable, or tool will significantly loses its tool life. So our aim is to keep the tool in the steady zone or the uniform zone, so that the tool wear will be very uniform or very stable, and also the machining output will be very good. So this is our aim, to keep our tool in this zone, right? Basically in this zone you can see that the tool wear is almost a straight line. See, you can see it is a straight line. So basically the flank wear, if you want to find the flank wear, then with time we can assume it to be linear, because we are assuming it to be on the stable zone. So flank wear can be written as one second. So if you are assuming it to be linear, then flank wear can be written as A plus BT. Why I have written this one? Assuming a straight line equation. Y is equal to mx plus b, right now? Y is equal to mx plus c. So here y is the flank wear, x is the t, and a and b are the constants, right? Why you are doing so? Because I am assuming it to be a straight line, nothing else. Why I am assuming it to be a straight line? Because I am assuming the flank wear happens only in the stable zone. Otherwise we can't take it as a straight line. Okay. Now next is the crater wear. So we can see this variation of crater wear with the cutting time. So we can see the crater wear the crater wear with cutting time, we can see it increases very drastically as the cutting time increases, and if the velocity increases, the crater wear increases very highly. This is the variation of crater wear with the cutting time. Okay, now we are going to tool life. So we have seen about that. We have seen about the tool wear. Now we'll see about the tool life. Tool life is a very important part of any tool, because our main aim is what? To increase the tool life. First, we should know what is tool life. How does the tool life define? Can anyone tell me what is tool life? Hello? Hello?
The time between two successive recurrents
Can you
of a tool.
Can you tell me like a very simple definition? Yeah, your definition is right, but like very simple definition I want.
Time in which tools give to desired function.
Right, right. This is a very simple definition. A tool that has no longer performed the desired function is said to have failed. Means the time up to which the tool perform its desired function is said to be the tool life of a tool. है ना? Then how you can there are different ways in which the tool failure can be identified. How? The wear land size, the depth of the crater, the tool wear volume, the magnitude of the cutting forces, the surface finish value, the change in the component size, the total destruction of the tool. These are the various factors because of which we can say that how is the tool life. For example, if we'll measure the cutting force using a dynamometer and very high forces are coming, we can see that the tool life is very less, or the tool has become very like the condition is not that good, because of that only the very high cutting forces are coming, or the surface finish is very low. Therefore we can say that the tool life is very not good, or the crater wear or the flank wear are very high, so we can say that the tool life is not so good. So these are the various factors by looking at which we can say how is the tool life of the tool. So what are the variable affecting the tool life? One is the cutting condition, tool geometry, tool material, workpiece material, and cutting fluid. So we'll see some of the factors which affects the tool life. Okay. Before that, we would see the Taylor tool life equation. It is the most important equation which is given by Taylor. So anyone knows what is the Taylor tool life equation?
Yes, sir.
Yeah, please say.
Dt power n equal to constant.
Okay, fine.
Where V
Yeah, please say.
cutting velocity,
Yeah.
T is tool life, N is tool life exponential, C is a constant for mission.
Okay, fine. You're right. Where V is a cutting velocity speed, T is a tool life, and N, C are constant. Okay. So from this equation we can say that tool life is inversely proportional to V, right? This means that if we increase the V, then our tool life will decrease. So therefore, but increasing V have other good factors also. For example, if we are increasing V, then our production will increase, because more cutting will happen. Our production will increase, but our tool life will decrease, because at a very high speed, very high temperature will develop, and high temperature will lead to high power consumption, leading to very low tool life. So therefore we need to find a very optimum V, so that we can maintain a good tool life, which we will see in the later section. What is the optimum amount of V to be obtained? Okay, fine. Yeah, I'll rub it. Also, we have a modified Taylor tool equation. Can anyone know what is the modified Taylor tool equation? Yes. Okay, yeah. Please tell.
So from Taylor tool life equation,
Yeah.
V equal to C divided by T to the power N.
Right.
or Tn equal to C divided by V.
Right,
Then P will be C nth root of V.
right.
So if we take nth root, then will it affect that much?
Yeah, it because yeah, it will affect na. It depends. The n depends upon the tool material. It depends upon
Hmm.
the n. If you are using
Hmm.
very hard tools, for example, ceramics or carbide,
Hmm.
if you are using very hard tools, the value of n is high. For example, it is from 1 to 2.
Hmm.
But if you are using very soft tools like HSS, then value of n is around zero point 0.8 something.
Hmm.
Then it will not affect that. So more harder the tool is, that more is the value of n, more it will affect. It depends upon the
Okay.
tool.
Okay.
Okay.
Okay, sir.
Okay. Okay. So I was asking about the modified Taylor equation. Do anyone know what is modified Taylor equation?
Sir,
Yes.
V2 power Vt power n
Uh,
F power x d power y plus c.
okay. Very good. So basically this equation is v power a, f power b, d power c, t equal to c. So why we came when we have a Taylor equation, why we there was a need of a modified Taylor equation. See, this Taylor equation only related the tool life with the cutting speed, but also we have seen that tool life also depends upon cutting speed, feed and depth of cut, right? So to bring the contribution of feed and depth of cut also in the calculation of tool life, this modified Taylor equation has come into existence. So therefore it also show how the variation of depth of cut and feed affect the tool life. The if we order the variation, then the highest contribution of is feed, second is of feed, and third is of depth of cut, D. Okay, fine. Now, can anyone can anyone take the log of this equation and plot the curve between t and v? Can you do this? Hello? Hello? Hello?
No, sir.
See, if I want to plot a see, this would be something, this curve would be something like this, right? If I draw a curve between t and v, it would be something like this, right? Like this. But you understand now why this curve is coming. If I want to draw a curve between t and v, see, I want to curve a draw between t and v, then this type of curve will come, which is a rectangular hyperbola. Rectangular hyperbola. This equation is like this only, na? X y equal to constant. So see, when you are increasing v, the t is decreasing. But if I want a straight line, for example, if I want a straight line, so how can I, what I can do so that I can plot a straight line curve between v and t? Do you have any idea? Anyone having any idea?
Log v on y axis, log
Yeah, right. So what we
t
can
on
do,
x axis.
right? What we can do, we can take a log of both sides. So if we take a log on both sides, v t की power n equal to log c, then this will become log a into b, log a plus log b. It will become log a plus log t की power n, and this log c is constant only, so I can keep it k something. So this will become n into log t into log v equal to constant, and this n log t will become minus log v plus k. If I'll bring n that side, then log t will become minus 1 upon n log v plus k upon n. So this is y, this is m, this is x, and this is c. It is y is equal to mx plus c graph. So when you will draw the graph between log V and here log T, you will get a graph like this. Why this? Because it has a negative slope. See, minus 1 by m is a slope, na? Therefore like this. So this graph you will get. Is it okay? Is it okay?
Yes, sir.
Okay. So similarly I have shown there कि this is the graph you will get. More will be the value of n. More will be the value of n. Then the steeper will be your curve. For example, if you draw here, okay, I'm giving you one situation, right? One is, see, log V and one is log T. I have three curves. One is this, one is this, and one is this. Can you tell me which one is ceramic, carbide, and HSS? 1, 2, and 3. Can you tell me which one is what, 2 is what, and 3 is what? 1 is ceramics. We have three material: ceramics, carbide, and HSS. Can anyone tell me?
One will be ceramic.
Okay. And one will be ceramic. Then yes, please tell. Simple it is, na? More
carbide.
yeah, 2 carbide.
Third one HSS.
Right. See, more harder is the material, more would be its n, right? And more is the n, then more steeper will be the curve. So therefore, first one would be ceramic, second would be carbide, third would be HSS. Fine? Fine, okay.
Yes, sir.
Now we'll see the tool geometry variation on tool life. How the tool geometry have a variation on tool life. First we'll see about rake angle. This is the explanation. We already know, we have seen before, if we increase the rake angle, the tool life increases up to certain region, and after a particular region the tool life decreases. Because what happen, if rake angle increases, then we know that if increase the rake angle, then the tool becomes sharper. Tool becomes sharper, and because of that the power reduces and the force reduces, and force reduces because of that. One second. Force reduces, because of that temperature reduces, and hence the tool life increases. But what happened, if we'll increase the rake angle above a particular point, then the tool strength will decrease. Therefore it is up to an optimum range only we can increase the rake angle. We have discussed this already. Increase the rake angle up to optimum range, the tool life increases. After that, because of the, if will increase further, then the tool strength will decrease, because of that tool life decreases. Therefore this is the optimum value of rake angle up to which the tool life is maximum. Fine? Is it okay? So I should move to the next slide, right? Okay. One is flank angle. So flank angle also have a similar observation compared to the tool life. If we'll increase the flank angle, then the tool and the workpiece distance will increase. Because of that, the friction will reduce, then power will reduce, then the temperature will reduce, then the tool life will increase. But however, when you increase the tool flank angle above a particular region, because of the same reason, the strength of the tool will reduce, and because of the tool life will decrease. It has the same reason of that of rake angle. More, see, this is the feed. So more is the feed, more is the tool life. Okay. Sorry. See, F1, F2, F3. See, if more is the feed, for the lesser feed you will have more tool life, because see, if you will have more feed, then the more force will, chip load will increase, so the more force will generated, tool life will decreases. So for if F3 has the minimum value of feed which have the highest tool life. So if feed is more, then tool force will increase, leading to tool life will decrease. So out of these three, the feed having the lower value will have the maximum tool life. Okay, fine. Next is the side cutting edge angle. We can see that the side cutting edge angle also, if we will increase side cutting edge angle, then the tool life increases, after that it decreases. For what happen? For the given feed and depth of cut, the length of the engaged cutting edge increases with increase in the side cutting edge angle. Right? Because of the length of the engaged cutting edge, the force or that load get distributed. Because of that, tool life increases. But above that side cutting edge angle, it will increase. It will reduce the strength of the tool, and because of that, that tool life decreases. See, I have given you one homework. Find why with increase in the side cutting edge angle, the temperature decreases. This gives you the answer. Now you don't have to do the homework also, because here only you got the answer. What happens if side cutting edge angle increases? So the more length of cut is engaged during machining. Because of that, if more length of cut is engaged, then the load distributed is very evenly. Like if you have a single point and the load distribution is very high, because of that force will increase, temperature will increase. But if you have a wide area, for example, if you have a single point, then it will have very high load. But if you have a particular length, then the load will distribute uniformly, right? Because of that, the force will decrease, temperature will decrease, and tool life will increase. The same reason. Now nose radius also we have seen what happened in nose radius. We know surface roughness is equal to f square by 8r. So if nose radius we will increase, means surface roughness is reducing. This means then the tool life surface is good, then the tool life will increase. Very simple. Okay. Do you have any doubt up to this? Hello?
No, sir.
Okay.
No, sir.
Okay. Now we have seen about the various factors affecting the cutting temperature, the tool wear, what are the different kinds of tool wear, what the tool life, what are the various factors affecting tool life, Taylor tool life equation, modified Taylor tool life equation, everything. Now talking about the talking in terms of the industrial point of view. When you are working in an industry or in any company, what is your aim? Your aim is to maximize the profit, minimize the cost, reduce the time. These only three aspects you are working on, right? Minimum cost per component. If you are producing some component, the cost should be minimum. Second, the production rate. In a very less time, you should produce large number of material. Third, profit criteria. You should get a maximum profit. So based on three criteria only, you design your material, tool, workpiece, parameters such that this three criteria are fulfilled. Right? Now, what happened if you want to produce a part? So what is the total time taken to produce a part? See, if T is the total time taken, which is equal to TL plus TM plus TC by NP. So what is TL? TL is the time involved in loading and unloading of the part. TM is the machining time per part. TC is the time required to grind the tool, and number of parts produced per tool ground. See, what happened? when you are doing a producing a product or you are manufacturing a product, total time it is required. One time is to load the part. If you want to machine some part, you have to load it now, you have to load it in some fixture on some table, that is TL. And then you, after loading, the tool will machine the part, that is TM. And then if you want to regrind the tool, if a tool you want to change it or regrind, that is TC. And how many parts are produced and at that time is called NP. This is the total time which you need to take care while designing the optimum process parameter. Now we can see here, see we are seeing the time with the cutting speed. See, if you increase the cutting speed, so what will happen? If you increase the cutting speed, then the cutting time will decrease. For example, if it take 1 minute to machine a particular material for a particular speed, if you increase the speed, then it will take less than 1 minute, right? So the cutting time will reduce. It is very good. But if you increase the V, we have already seen, then power increases, temperature increases, tool life decreases. Because of that, if increasing the V, tool life will reduce, then the tool will loses its life very early. Then you need to change the tool. Then the tool change time will increase. If for example, for a particular speed, your tool life is 1 hour, for example, then because of increase in speed, it can reduce to 50 minutes. Now 10-minute tool life has been reduced. Then after 50 minutes, earlier you were going to change the tool after 1 hour, but now you are going to change the tool at 15 minutes. So that 10-minute life is also reduced. Now tool change also you have to do. That will take more time. So if in 2 hours, if earlier you were doing 2 times tool change, now you are doing 3 times tool change, then the tool change time increases. So we can see with increase in the speed, the tool change time increases. However, the cutting time decreases. Therefore, we need to find the optimum V. This is the actual curve. We need to find the optimum V which take care of both things. That V max is the optimum V that takes care of the optimum value of the cutting time and the tool change time. So we need to find that V, right? See, there are formulas where you can find TM, NP, everything. So see, for find the minimum time, ultimately you find the minimum time. So what we have this T, right? We have this T. So what to do to find the minimum? We will differentiate it and we will take the minimum of it. So what we will do? We will differentiate this T with V and put it to 0. Right? Now you can put the value of other parameter. For example, TL, you can put the loading time would be given. TM is the machining time, which can be found by L by Fn, and this TC would be given. NP you can find by this formula. So putting this formula, ultimately you are getting 2 conditions. One is a V optimum and one is a T optimum. This optimum condition of V, which is the cutting speed, and the tool life, is for the maximum production rate. When you want a maximum production rate, then what should be the optimum cutting speed and the optimum tool life, so that you'll get the production is maximum. So this 2 formula you need to understand. You need to learn. Ki V optimum is C upon 1 by n minus 1 into TC ki power n. And T optimum is 1 by n minus 1 into TC, where TC is the tool change time. TC is what? Tool change time or regrinding time. Whatever you say. Tool change time or tool reground time. Tool change time in minutes. Understood? You should know these two formulas, so that for the maximum production rate, you can find the optimum cutting speed or optimum tool life. Okay? So this is clear up to this. Hello?
Yes, sir.
So you have any doubt for this session? Now, if you are okay, then we'll move to the numericals part. Can we move to the numerical part?
Yes, sir. Yes, sir. Numerical parts.
Okay, fine. So today we will solve like some of the numericals, which will help you to help you in the assignments. So first, question number 1. Please read it. In an orthogonal, whatever you read, just write it. in an orthogonal cutting with a tool of 8-degree rake angle. So alpha is how much? 8 degrees. The cutting force Fc is how much? 450 Newton. The thrust force Ft is how much? 400 Newton. Cutting ratio R is 0.75. The cutting velocity V is 75 meter per minute. The power dissipated due to plastic deformation. The power due to plastic deformation. Can you find this?
No, sir. Actually, thrust force is 350.
What?
Sorry.
Please try for 5 minutes, then we'll discuss. Please everyone try for 4-5 minutes. Try to think how to, first you think which power it is asking. We have two power. One is the power because of the rake surface and one is power due to the shear zone. So which power it is asking? Please think that and then think how to find it. Just do it. I'll give you 4 minutes. Are you able to do this? Hello?
Yes, sir.
So anyone has done this?
Just wait, sir.
Okay.
Four hundred 30 watt,
431.
31 watt, 30 watt, 430 watt.
Okay, 430. Anyone else?
Sir, 17 kilowatt.
How much?
17 kilowatt, sir.
17 kilowatt.
Yes.
Okay. Anyone else?
266, sir.
How much?
266.
Okay. Okay, let's see. Those who have solved, please check your answer here. See. First of all, in this question, we need to understand which power it is he is asking. See, we have total. We know the total power. Total power is the summation of two power. One is the power because of the chip, and one is the power because of the shear, right? This chip power is the power because of the when the chip flows on the rake surface, and this chip power is the power when the chip gets sheared on the shear zone, right? Hello.
Yes, sir. Yes.
Okay. So if it's asking the power dissipation due to plastic deformation, this means it is asking about the shear zone. Means it is asking about this power P shear. So ultimately you can find this P shear equal to P total power minus power due to chip, right?
Yes.
Now let's calculate each and everything. So total power is how much? Cutting force into cutting velocity. So cutting force is how much? Cutting force is 450 Newton and cutting velocity is 75 meter per minute, but we want the watt to be in watt or kilowatt, so we will divide it by 60 to make it meter per second, right? It would come around 562.5 watts. Now we need to find the power due to chip. So we know that the chip flows on the rake surface, and rake surface, which force we have? We have the friction force, right? Then it should be F into Vc, where F is the friction force, Vc is the chip velocity. Also we know that Vc is equal to R times of V. This means that friction force into R, how much R is there? 0.75, and how much V is there? 75 by 60. This means we need to find the friction force now, right? So how to find the friction force? We know this formula of finding friction force. Friction force is how much? Fc sine alpha plus Ft cos alpha, right? We have Fc, we have Ft, we have alpha. Just put it and find the solution. So you will get, after solving, the friction force to be around 458.7 Newton. Have you got this? Hello?
Yes, sir.
Huh.
458.74.
Right. Then just put this in the P chip. Then you will get P chip is equal to 458 into 0.75 into 75 by 60. How much you will get?
430.
430. 430.06 watt. One of the student was telling 430 answer, right? But what you have to find? Your answer is not 430. You need to find the P shear. So your answer will be this 562.5 minus 430. So your answer will be around 562, not, sorry, 1 second. Your answer will be 132.5
Yes, sir.
watt. Understood this question? Hello? Everyone understood this question? What mistake you
Yes,
were
sir, yes.
doing? Hello?
Yes, sir.
So basically you need to first understand which power it is asking. To the power due to plastic, if it would have asked calculate the power dissipation due to chip, then the answer would have been 430, right? But it has asked the power dissipation due to plastic deformation. This is clearly saying the power lost in the shear zone. So therefore you need to calculate total power and subtract the chip power. So total power is calculated by using Fc into V. You have given everything. Now for chip power you need F into Vc. So Vc is R into V, and F you have formula Fc sin alpha plus Ft cos alpha. You find the chip power, you have total power, subtract total power from chip power, you will get the shear power or the plastic deformation power. Fine? Okay, then I am moving to the next question. Fine. You have any doubt, then please ask, otherwise I will move to the next question.
Okay, sir.
Okay. See, this question is for everyone. In a machining operation, average cutting temperature increases with increase in what? Say, please read the option and tell me the answer. Please tell me the answer.
A, C, and D.
A, C, and D. Okay. Anyone else? Yeah, you have right. We have already seen that the average cutting temperature increases with the cutting speed, depth of cut, and feed. The answer is A, C, and D. Sorry, A, C, and D. Fine. Okay, so let's move to the next. This was very easy. Let's move to the next question. This third. Please read the question. In an orthogonal cutting with a tool rake angle, so alpha is 9 degrees, right? The cutting force, which is Fc, which is equal to 300 newtons. The thrust force Ft, which is equal to 200 newton. The cutting ratio R is equal to 0.7. The cutting velocity is given 65 meter per minute. The power dissipation due to friction. The power due to friction it has asked. It is now very easy. Can you do it?
Yes.
Please try it. Please try it and tell me the answer.
One 185.39.
How much?
185.39 watt.
Okay, fine. Okay, let's see how to
Power
solve.
dissipation due to friction means chip power.
Right. Chip power. This is the chip power. So we know chip power is how much? Friction force into the chip velocity. So we know friction force how to calculate. Fc sin alpha plus Ft cos alpha. Just put the value 300 into sin 9 degree plus 200 into cos 9 degree. But what value you are getting here?
244.47.
Okay, 244.47 Newton. and then need to calculate the chip velocity. Chip velocity is how much? R into V. So R is 0.7 into V is 65 by 60 to convert into second. How much this is coming? 0.758. Therefore, the friction power is how much? This into this, 244.47 into 0.758. What is the answer? 185 point something, na? Fine. Hello. Is it okay? Can I move to next question? Hello.
Yes, sir.
Okay. So please answer this question. In which of the following zone the average temperature rise is the maximum during machining? Please answer the question.
Yes, sir. Chip tool interface.
Okay. Anyone else? See, basically we know that the shear zone has around 80 to 85% of the heat, है ना? And chip tool interface has around 10 to 15% of the heat, and the tool workpiece have around 5% of the heat, right? So the answer would be the shear zone. But also here, like also B option can also be considered because it also has a significant amount. So if in a multiple choice question you can answer both A and B. However, for a single answer it would be A. Fine. Hello. Hello.
Yes, sir.
Yes, sir. Yes, sir.
Any doubt? Can I go to next question, na?
Yes.
Okay. See, please answer this question. Which one of the following condition is the most favored for reducing the temperature generation in a machining operation? Small positive tool rake angle, large positive tool rake angle, large negative tool rake angle, small negative tool rake angle. Please answer this. Which is responsible for the reducing the temperature? Please relate how the temperature is related with the rake angle.
B, sir. Large positive rake angle.
Why read so? Why you are saying this?
Increasing rake angle, decreasing the forces.
Right.
Power consumption decreases.
Okay, very good. The answer is B. Because if rake angle increases, we know that the rake angle increases, then the force reduces, power reduces, then the temperature also reduces. Right? Everyone is okay with this? Hello?
Yes, sir.
Can I go to next question?
Yes.
Attrition is and galling are the type of which wear? We have seen this. Please answer this.
Adhesion.
Addition.
Right. This is very simple, na? Adhesion. Fine. Answer is D. Okay. 7th question. Please solve this question. In a steady wear zone, at the end of 15 minutes, flank wear was found to be 0.4 mm and it was 0.6 mm at the end of 20 minutes. Assuming a failure criteria of 0.9 mm flank wear, the estimated tool life is. Please solve this question. Please try to solve yourself, then I will discuss with you. Please try to solve it. Please read the question very carefully. Please, this is a very good question. Please try to solve it. I'm giving you 5 minutes.
In a steady wear zone, it's like a straight line.
Right. Exactly. You need to because in steady wear zone, this is the graph, na. This is the graph. It is there. So in the steady, it is like a straight line. So you should assume it is a straight line equation and solve it. Okay.
Okay. But 27.5 minutes.
How much?
27.5 minutes.
Yeah. Okay. Anyone else? Anyone else? Okay, then we'll solve it. See, it has told about steady wear zone, and I have discussed that in steady wear zone, the length of the tool, this flank wear can be considered as a straight line, right? So I'm assuming it to be a straight line. So length of wear should be around a. I'm assuming a constant to be a plus bt. ठीक है. Now it is said for 15 minutes the flank wear is 0.4. So it is 0.4 for a plus 15b, equation number 1, and for 20 minutes it is 0.6. So 0.6 equal to a plus 20b. Okay, equation number 2. You can solve this two equation. What is the value of a and b you are getting?
A equal to
Yes, what?
minus 0.2
A is minus 0.2,
and B is 0.04.
0.04 mm, है ना? Actually it is in mm per minute, because then only it will cancel out with time, na? Understood na why I have written here mm per minute? Because you need to find L in mm, na? And A is directly, but B is multiplied with T na. Then mm per minute into minute it will become mm. Okay, now what you have to do, find the tool life, assuming the failure criteria to be 0.9. This means at 0.9 only the tool will be life will be over na. Then for 0.9 just put the value minus 0.2 plus 0.04 into T. What is the value of T coming? What is the value of T coming?
27.5.
27.5 minutes.
5 minutes.
Okay. This is the answer. T is 27.5 minutes. Have everyone got this?
Yes, sir.
Okay, very good. Very good. So, like, can I move forward or anyone having any doubt?
Forward.
Okay, fine. See, the next question, this is also very good question. Here, Taylor tool life equation is Vt, this is power 0.25 equal to 550. Right? 550. Where V is a cutting speed, tool is a tool life. A fresh tool is operated at a cutting speed of 200 meter per minute for 20 minutes. Okay. After that, the same tool is operated at the cutting speed of 120 minute per till failure. The total time of machining by the tool is, okay. This is the equation. It is saying for first 20 minutes a fresh tool is operated for with 200 meter per minute, and then after the same tool is only used for 120 meter per minute till failure. The total time of machining by the tool is, please can you calculate this? Please do this.
Just try, sir.
Okay, I'll give you 5 minutes, do this. Have you got the answer?
Answer is 461.29.
How much?
461.29.
441.
461 sir.
461. Okay.
जी 0.29.
Anyone other than? Please read the question properly. Total time of machining of the tool.
One 154 sir.
How
154
much?
minutes.
154 minutes. Okay. Let's solve it. First, using this equation, calculate the tool life for 200 meter per minute, right? So what we'll do? 200 into T 0.25 into 550. From here, how much you are getting tool life? 57 something, na? Something this much you are getting, right? Hello? Hello? This you got? Hello?
4.58 sir.
What?
4.58.
Nee, this you solve this, na? After solving this, how much you are getting?
57 something.
Right, 57 something you're getting, na?
Yes sir. Yeah.
So this means ki 50 when you are doing the machining with 200 meter per minute, your tool life is 57. है ना? When
Yes,
you are
sir.
machining with this particular speed, the total time it can machine 57 minutes. But out of this 57 minute, 20 minutes you have already machined.
Yes sir. Yes sir.
Then how much is left? 37 minutes is left, na?
Sir plus.
Wait. Please try to understand. This question is how total time of machining by the tool. It has not asked the total tool life of the tool.
Okay.
That it has not asked the total tool life. It has asked ki how much time the tool will machine. Machining. Tool life can be more, but it is asking the total time of machining by the tool. If you are machining, then what is the total time the tool has machined? Right? So 57 is the total tool life. Out of it 20 gone. How much left? 37. 37.19.
Yes sir.
Okay. So 37.19, if you will divide by 57.19, you will get 0 point something. How much you will get? 0.25. Answer is 0.65. So this is the factor. This is the factor. This is the remaining fraction of the tool life. You are understanding this? Hello? See, 57 is the total tool life. Out of 57, 20 time has been already done, 20 machining, so 37 left. To determine the fraction where the machining is not done, which is the leftover time upon total time, na? So 37 upon 57 is 0.65. This 0.65 is the fraction of tool life which has to be machined, which is not machined yet. Right?
Yes sir.
Now let's calculate for 120 meter per minute. What is the tool life coming? Just put V into T 0.25 into 550, where V is now 120. How much you are getting T now? Something 441 something. 441 something.
441.
है ना? 0.29. See, now this tool life, this is the total tool life when you will machine from 120. This is the total tool life. But actually, you would see कि only this fraction of tool life is left, na?
Yes sir.
So you need to multiply this by this to get the actual tool life. because this is giving the tool life from starting, but actually you have already from start, you are not using the tool from starting na, you have already used it for 2 minutes for 200 meter per minute. Therefore you should multiply this into 0.65 to get the actual tool time, which comes to be around how much, 286.8 minutes. So this is the actual time you are machining, plus you have already machined 20 before, so your actual time will be 286 plus 20, which is around 306 minutes. Have you understood this?
Yes, sir.
I am explaining it once again. See, it is asking the total time of machining. It is not asking the total tool life. It's asking total time of machining. So first you are using a fresh tool and using this 200 meter per minute, you are machining 20 minutes. So I am calculating for this 200 meter per minute what is the tool life. So tool life comes to be 57. Right? But out of this 57 minutes, 20 minutes have already been machined. So we are, so how much time is left? 37. So 37 divided by total time is this 0.65, the total fraction of time which is yet to be machined. Right? Now I am calculating the tool life using 120 meter per minute. So if I reduce the speed, tool life has increased. But this is the ideal total time from the starting. But we have only 0.65 left. So we have multiplied this by 0.65. So we get the total tool, this is the time of machining. And also 20 has been done before. So we will add 20 here. The answer is 306. Okay?
Yes, sir.
Anyone having any doubt, please ask. Or we'll move forward then. Okay then?
Okay, sir. Yes.
Okay. See, the next question is tool life for a maximum production rate. When the tool life is itta, where n is given to be 0.3 and tool changing time TC is given to be 10 minutes. So you need to find the tool life for the maximum production rate. So we know that for maximum production rate, the tool life optimum value is how much? 1 by n minus 1 into TC. Right? Just solve it. Please solve me and tell me the answer. There is a direct formula used na for this.
Sir, 23.33.
23.33.
33.
This is very easy. You just need to
Yes.
put in the formula.
Yes.
Okay, the final question for today's session is a cutting fluid should have. Please read the option and tell me the answer.
Yes, sir.
A. Why A?
It should have high specific heat, sir.
Why it should have high specific heat?
It evaporate faster, sir. If specific heat is low.
Okay. And high thermal conductivity and low volatility. Okay, see, specific heat is how much? Key amount of heat required to increase the temperature of a substance by 1 degree, by unit degree temperature, right? So if we'll have a high specific heat, then more heat will be required to raise the temperature, which is a good thing, right? The temperature will not temperature will not be raised very like from a small heat only. So we require a cutting fluid should have a high specific heat, so that if because we want the cutting fluid to be stable, right? So if for example in machining the cutting fluid temperature will only increase, then how it will provide the required lubrication and coolness to the tool and workpiece. Therefore we want it should have a high specific heat. Second, it should have a high thermal conductivity because we want the cutting fluid to not carry the heat. If the thermal conductivity is very high, then the fluid will not carry the heat, it will pass the heat. So we require that. And third, obviously we require the low volatility for the proper stability. So it should have a high specific heat, high thermal conductivity and low volatility. Okay, fine. Also one more point is that it should have very high flash point. High flash point. You know what is this? What is high flash point? Anyone knows? Flash point is that particular temperature required when the cutting fluid burns. So if it has very high flash point, then you will require very high temperature to burn it, and we want that only. It should not burn from small spark or temperature. So it should have a very high specific heat, very high conductivity, low volatility and high flash point. Okay?
Yes, sir. Yes.
Okay then, so we will be closing this session now. If anyone having any doubt, please tell me here.
No, sir. Thank you so much, sir.
Okay, sir. Okay, then I'll be uploading this lecture on YouTube. The name of my channel is Abhishek's NPTEL tutorial.
Okay.
I'll be uploading this lecture there. If you are having any doubt, you can watch there. And please please do complete your assignment 5 before the deadline. And all the best. We will meet next week. Okay. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.